All right, so I hadn't seen any of you guys posting questions about the worksheets for assignment 4 or assignment 5. I was looking for them down here in the comments underneath the individual assignments themselves. Most of it's vocab, so I didn't expect there to be too many, especially after having posted the walkthrough for the first half of assignment 3. But I wanted to show you where you could find all of the answers. Here on Edmodo, because I do have them all posted at this point. So if you guys go up into your folders tab right here, you can go down to Unit 12, Simple Harmonic Motion. And in this little scroll down window, you'll be able to see everything for the entire unit. Here's the answers to assignment 1, assignment 2, 3, 4, and 5, all posted. I posted some of them today, but that's fine. That's what I promised I would do. Here's the supplemental packet if you still want to give it a shot. Again, it's an additional resource. It's still available to you. It's really good for those real quick wave calculations that some of us were initially struggling with last week. You'll still see in your upcoming assignments right here where you can deposit the information for all of the assignments. So if you had assignment 3 and you wanted to submit assignment 3, all you would have to do is type in anything that you want to type, like a quick response or something like that, and then go to attach. Attach wherever it is that you need to, usually from your computer, or you probably do this through your phone as well. But that is it. That's how you guys would operate that. So for assignment 4, what I wanted you guys to recognize was obviously we split this unit in half, trying to make it a little bit easier for you guys since we're doing our remote learning shenanigans. But if you guys scroll down and skip over the pendulum and spring stuff, because we've already taken our little mini test on that, you'll get down to either number 7, which you can try because it's just a period versus frequency problem, or number 8. With number 8 being provided, I gave you the speed of sound. We'll talk about how we calculate all of this. It's based on temperature. That'll be next week. Then you were provided with the wavelength and asked about frequency. So you're just going to use our basic wave equation. Velocity is equal to wavelength multiplied by frequency, divided by 4. There you go. For number 9, you've got both a frequency and a wavelength. One of the things I wanted to mention was a lot of folks, when we go to take the exams, like to think that velocity is dependent upon wavelength and frequency. It's not. While you can use properties of wavelength and frequency, if you know both of them, to calculate the speed of the wave is determined by the medium that it's trying to travel through. So while you can calculate it using wavelength and frequency, and there's a relationship there, for the quiz and mini test, what I want you to remember is that velocity is determined by the medium the wave is traveling through. And we'll talk about that a lot more when we get to sound and light in the coming weeks. In this case, all you needed to do is 10 multiplied by your 0.05 hertz, and you should be set, ready to go. I apologize for 10 being a little fuzzy, but you're trying to solve for the period that these objects have as they bob up and down in the water. I gave you a frequency. 8 times every minute is still a frequency, but remember that we need it to be in seconds. So all you would really have to do here for letter B is instead of 8 times divided by 1 minute, you would divide it by 60 seconds. That will give you a unit of hertz. You can do cycles per minute, but then your unit isn't going to simplify to be hertz. It'll be cycles per minute. And when you go to calculate your period from that frequency, your period will be measured in minutes. So if you had a period measured in minutes, it's probably a very, very, very small value because this is only 7.5 seconds. You could do the inverse equation for period is equal to 1 over the frequency in order to find your period, or I simply prefer inverting what I had been given. So you were given 8 cycles every minute. So flip that on its head. It's 1 minute for every 8 cycles. So 60 seconds divided by 8 is going to give you 7.5 seconds per cycle. From that, make sure you know which one it is you need to be using. You need to be using your frequency, not your period. So 7.5 should not be anywhere in letter C. I see that a lot. It's one of the more common mistakes. Make sure you know which one is frequency, which one is period, and plug them in, plug the correct one into this wave equation down here. From there, number 11, yet again, it was a frequency that was given to you. It's the number of times this thing occurs divided by the number of amount of time, that it occurred for. That's how you'll find your period and your frequency down below. Amplitude isn't going to change, but from trough to crest, if it's 9 meters, remember that your origin is halfway in between those, and you measure amplitude from the origin. So it's 4.5 meters, I believe. Yeah, I had gotten that wrong down there. So it should have been 4.5. Down here, If you're getting 325, I had a couple people emailing me saying they got 325, wanted to know if they were wrong. Really, all it comes down to is I kept a value in the thousandths place because 6.5 and 0.02 are such drastically different numbers. That extra little significant figure there at the end of my frequency provided a little bit more detail and clarification and gave me a more accurate value for what this wavelength should have been. Also, I messed up my units here as I'm looking at that. That should have been explicitly meters, so get rid of the per second part. But your wavelength should be around 295. If you got 325 because you just did 0.02, that's fine as well. Just be aware that if you show me your work, you'll never get it wrong because 325, if you didn't include that second two, that last significant figure would still be correct. All right, so last assignment for this week was assignment 5. That was a typo right there. Should have said assignment 5, but it was your review. I wanted you guys to work on the vocabulary because that's a big part of this. We'll use these vocab terms as we progress through our next 2 units about sound and about light and all the weird things that they do. So knowing that, really the only part of it you're going to need for this week in terms of the equations are up here. You've got one version of each of those equations, regardless of what I ask you on the mini test or on the practice quiz. You guys should be able to pick one of those. Obviously, this one solves for velocity, frequency, and this one for wavelength. Use them. That way you don't have to worry about any of those solving for a variable in the denominator sort of issues that some people encountered from before. Your chapter 14 vocabulary, this encompasses everything from last week and this week. So period, we're doing a lot more interference stuff this week. Nodes, we decided to introduce this week as well because they're going to be rather important when we talk about our standing waves. And that's going to be big for sound. Remember that waves carry energy from a particular location. They don't actually carry individual particles or matter. It's like people at a baseball game doing the wave in the stands. The individual person doesn't make the trip around the stadium, but the energy, the wave itself moves from location to location. That was always a really good analogy that I would have used a bunch in class had we been together for that. Knowing the difference between longitudinal and transverse is going to be a big deal. Longitudinal waves are examples of sound, and then transverse waves are examples of light. So we'll talk about both of them again as we progress throughout the remainder of these next couple of weeks. I'm assuming we're going to go into May. I don't have anyone telling me that we are, but it's a gut instinct, I guess. And if we don't, then that'd be awesome. We'd actually be able to talk in class about all this. Number one, I expected to have a little bit of issues for this conceptual review part, and a lot of it just comes from people forgetting what defines a wave. If we go back to our pendulum stuff that we did in the pendulum lab, a complete cycle was when the pendulum bob went forward to the other end of its swing and then came back to where it started. That's what begins a full cycle and ends a full cycle. So if we're starting for all of these right here, what would initially be a node, and then this wave progresses through a crest and then back through equilibrium and then down to a trough and then back to equilibrium. Now we're back where we started and would repeat our motion that we had already begun over here on the far left. That means that this portion right here is one full wave, right? Going from node to antinode, node to the negative antinode, all the way up back to the node, to the origin. Origin to crest, origin to trough, back to the origin. Where you repeat yourself is where the next wave begins. So here, because I've got one full wave, and then I go from origin to crest to origin, that's half of a wave, I've got 1.5 waves represented right there. Letter B is one full wave. Again, we go from origin to trough, origin to crest, and then back. So this is one full cycle, right? It wound up right back where it began. Letter C has one full wave here. This is where the first wave ends. Your second full wave would end right here. And then again, you go from origin to crest to origin. That is half of a wave. You would have to have the crest after that to make it another full wave. So you get 2.5 waves present there. And then letter D is just half of a wave. It's the positive half as opposed to the negative half that would contain the trough. It's only one individual segment, half of a wave. Your biggest amplitude is going to come from letter A. Again, amplitude is from origin all the way up to your maximum. You'll notice that that is the tallest set of waves that you have there. If you wanted to measure them, go for it. That's cool. Shortest wavelength is going to come from the wave with the highest frequency, and that's going to be letter C. You'll see the distance from crest to crest is very, very small. And remember, you can measure wavelength from anywhere, crest to crest, trough to trough, or where the wave begins versus where the wave ends. Any of those three distances would count as measuring your full wave. It's literally just from wherever you begin back to that same point. And then the longest wavelength would obviously be letter D, because in the same segment of time, for each one of these individual waves, you only have half of that wave. So that one's going to be significantly longer. You would have to double what is present, get that trough included in there, and then that would be your full wavelength. For your mathematical relationships between period and frequency, this was actually letter A from first semester. This is something we did in circular motion, so I wanted to point that out. It's not new. They're inversely proportional to one another. When you're talking about wavelength and frequency, they too are inversely proportional. There were a lot of questions on the practice quiz that you'll be doing. That's due tomorrow at midnight about wavelength and frequency. The higher the frequency is going to be, the smaller the wavelength has to be, and vice versa. Wavelength and period, it's the exact same idea. This equation actually came from, if you wanted to have an equation that has wavelength and period in it related to speed, it is this guy right here. All I did was replace frequency in V equals wavelength multiplied by frequency with 1 over t, and you get wavelength over period. Again, number 3, this one pops up a lot. That's because it's a really, really, really big deal. Waves carry energy from location to location, not individual particles from location to location. And then number 4. Number 4, you've got without moving, changing the distance your hand moves. If your hand moves up and down the same distance, or left, right, same distance, your amplitude is going to remain the same. That was a description of amplitude. The phrase faster and faster means that you're getting more waves in there per second, which means you have a much higher frequency. High frequencies mean shorter amount of time per wave because you've got more of them in there. Again, those are inversely proportional. That was described in 2A. And then 2B described wavelength and frequency. If you have that higher frequency, then you're going to have a shorter wavelength, again from 2B. Velocity, I left blank because I wanted to remind you yet again, velocity does not depend, where did I have that? Oh, it's assignment 4. Velocity right here does not actually depend on wavelength and frequency, despite them being in an equation together, and you can use wavelength and frequency to find velocity. Velocity is determined by the medium that that object is traveling through. That was one of your key vocab ideas or vocab terms, concepts from chapter 14, and it's going to show up again in sound. So I wanted to point that out once again. All right, now for the whole reason that I had you guys watch those videos with the flippin' physics guy. Looks like Weird Al. He looks really awesome. I love it. The more I watch him, I mean, he's got great content. The more I watch him, the more I love it. He's having fun. Anyways, it gets to standing waves, how standing waves are generated. These are, again, important because this is literally the foundation of music. Why things sound the way they do when you hit a certain, place your finger at a certain position on the fretboard for a violin or a guitar. Why the openings and the valves in a trumpet or a flute, or the position that you have to move your arm on a trombone slide, why those have to be so specific. Otherwise, you'll get the wrong note. It has to do with generating these standing waves and getting a little bit of resonance, that buildup of the amplitude, so that it gets a little bit louder. We'll talk about it more later, but standing waves in general, when a wave strikes a rigid boundary, a wall, whatever it might be, the returning wave is going to be inverted. That inverted returning wave, if it returns and interferes with the incident wave, the original wave, basically, if they both have the correct frequency and they perfectly constructively interfere with one another, you'll get a standing wave, just like they showed in the videos. So that standing wave is going to have a couple of features. You're going to have nodes and antinodes. Those are going to be, the nodes are going to be regions where it doesn't appear that that medium is moving at all. If you envision this to be a guitar string or the string of a violin or a cello, nodes are where you're going to be placing your fingers on the fretboard in order to change the length of the string. And there's a whole equation that we would have done in class together. But I cut it because this is remote learning stuff and I don't actually get to be there with you guys to teach you the nuances of it. But the longer the string, the deeper the sound, the shorter the string, the higher pitch the sound. And so, the fretboard is always going to be your indicator where you place your fingers, and that's always going to be at one of these individual nodes. Antinodes are going to be the regions of maximum amplitude. I like to remember that, antinode, amplitude. That's where it's all maxed out at. They both start with the letter A. I think it's helpful. At position P, this was a lot of what he went over in the video as well, and this was the point of assignment 3. You don't need to do any of those weird waves that you saw in number 3 or 4 for assignment 3. We're not going to do any of those. All you need is the main idea. If you have two waves coming at one another that both have positive amplitudes, then the wave gets larger. In this case, if it's a positive 1 and a positive 1, it'll be positive 2 would be your amplitude right here at point P. If this were a positive 2 and a positive 2, then your amplitude when they overlap would be a positive 4. Literally just gets larger. If we had replaced this guy over here with a negative 2 for number 9, then you'd have a positive 1 amplitude, negative 2 amplitude, and that would give you a much smaller resulting wave. Now, if it were positive 1 and negative 1, they'd cancel out perfectly. You'd have no wave at all. It would be a straight horizontal line. But if they're not the same, you'll still have destructive interference. It just won't be perfect. There will be a little bit of a smaller wave there. And then number 10 was just, do you know the parts of a longitudinal standing wave? When longitudinal waves, like sound, travel outward throughout the world or through the atmosphere, it's regions of compression. I like to think of this as people shoving each other at a concert. Everyone wants to try and get up towards the front of the stage. If you've ever been to, I don't know, this happened to me a lot at Rise Against or Flogging Molly or any of those other concerts. Maybe if you've been to something like Riot Fest or know people who have, when people start shoving each other, individual people, like this line at letter A, don't jump to the front where the stage is at. They just fall into the person in front of them, and they fall into the person in front of them, and them into the person in front of them. It's a long chain of dominoes. That's literally what sound is. And so those regions where those particles are pressed together, squeezed together, are going to be compressions. They're analogous to crests in a transverse wave. The transverse wave you're more familiar with seeing in junior high sort of physics. And then the regions where there's more space in between them are going to be your rarefactions, maybe where people are getting up, breath dusting themselves off, and then someone shoves again, and the whole thing starts all over. But those are your two parts. I wanted to label them here because we'll talk about these a lot more when we get to sound and we talk more about longitudinal waves. But if you get the basics and you understand you can identify what they are, that's really all you need for this week. So yeah, that's it.